if n and 1 is equal to 1, number is odd, otherwise it's even. It should give me, this should give me true, because 67 and 1 should give me 1. And that is odd. True. If I try something like 68, 68 is odd. No, it's not. It will give false. Very simple stuff. All right, let's move forward to the next question. One more thing I want to mention, this last digit is known as LSB, least significant bit. This is known as LSB, least significant bit. Okay, cool. Question number 2. So a very important question. This question is, you are given an array of numbers, and in that array every number appears twice, only one number appears once. You have to find that number. For example, array is given something like this: 2, 3, 4, 1, 2, 1, 3, 6, 4. So you can see 1 is appearing twice, 2 is appearing twice, 3 is appearing twice, 4 is appearing twice, 6 is appearing once. This is my answer. How do we find this? Try to pause this video and think about it. Always in interviews, try to give the brute force solution first, discuss the complexity of it, and then do the optimized solution. So what is happening over here? What can we do? You can sort this array and then you can check, right? It's going to take m log n and n log n. That's how you can sort in n log n. It's also going to take some space complexity, because merge sort, quick sort, we'll learn about it later, take some complexity. So how can we do this? Try to think about it and then come back to this video. Well, before starting this question, there's one thing you have to understand. You know, these bitwise operators, like, you know, your normal like the mathematical operators, they also follow the associative property. So if I say something like, you know, 5 into 3 into 5 into 4. So if I say 5 into 3, something like this, and then 5 into 4, this is also equal to something like if I say 5 into 3 into 4, something like that. Okay, this is also equal to 5 into 4 into 3 into 5 is also equal to 4 into 3 into 5 into 5. So the order basically does not matter in simple terms. Okay, similarly, if I'm saying 2 XOR 3 XOR 3 XOR 4, this is equal to 2 XOR 4 XOR 3 XOR 3, or whatever. Similarly, for like all the bitwise operators we've talked about right now. Okay, now how do we solve this problem? It's very simple. So you can use hash map or whatever you want. Like we'll learn about hash maps later on. But let's say we don't want to do it in constant time and in just one single pass. Okay, O of n complexity. So you know that this particular point, the point I've written in red. All the important points I've written in red. This one. Any number XOR with that number gives 0. And 0 XOR any number gives that number itself. 2 points. So if I 0, any number XOR with that number gives 0. And 0 XOR any number gives that number itself. 2 points. So if I XOR Welcome back to another video, and this is the second video for the maths for data structures and algorithms. And we've already done one on complete bitwise operators. And if you're new to the channel, make sure you like, share, and subscribe because we're doing a complete data structure algorithms bootcamp. But in this video, we'll learn about a bunch of things, very important concepts like prime numbers, some of the various methods to find a number of prime numbers, efficiently. It's called the sieve method. We'll learn about that. We'll learn about a square root method. We'll learn about how to find, let's say, factors of a number. We'll learn about some modulo properties. We'll learn about HCF, LCM, and Euclidean algorithms. I'll actually teach you what does it mean, like in words. What do we mean by HCF, LCM? Might not have heard about it. You might have heard about it. But let's see if we can find out. So let's get started with the prime numbers. So we've already covered like prime numbers before when we were doing like first Java program. So you can watch that video, and we were doing like flow charts and stuff. Then we were learning about prime numbers over there. The prime number, as we all know, let's say we learn about prime numbers. So prime numbers. So what are prime numbers? A number that is divisible by 1 and itself. Obviously every number is divisible by 1. So a number that is divisible by 1 and itself is known as a prime number. So example 2, 3, 5, 7, 13, so on and so forth. Okay, so that's the condition. A number should only be divisible by itself and 1. So it means that number, let's say if I'm talking about 13, so ignoring the number 1 and 13 itself, all the numbers that come in between. Okay, so for example, all the numbers from 1 and 13 are what? Basically, you're trying to figure out if a number is given to you, how do you write a program to find whether that number is a prime number or not? So given number 1, so given let's say number 13, you have to find 13 is prime or not. Write a program to find whether 13 is prime or not. You're like, okay, all the numbers that come till 13 are like this, something like this. We know that if we're trying for 13, we should ignore this one, and we should ignore this one. If any of these numbers divides 13, then 13 is a prime number. Because obviously a number greater than 13 will not divide 13, right? Yeah. 13 into something should give me 13. So 13 into 1 gives me 13. Some other number into some other number should give me 13. Okay. 13 divided by some number should give me some number, integer. Is there any possible number that allows us to do that? Because I know 13 into 1 is 13. Okay. That's fine because we are ignoring that. We are ignoring 1 and we are ignoring 13. Second is any number into any other number can give me 13. Similarly, can be 13 divided by any number should give me some other number. So we're going to check. Is 2 dividing 13? No. Means if I divide 13 by 2, is the remainder 0? No. Is 3 divided by 13? No. Is 3 dividing 13? No. 4? No. 5, 6, 7, 8, 9, 10, 11, 12? No. Now can you write a program for this? Can you write a simple program for this? You can say for I is equal to 2, I is less than n, I plus plus. If the number n is divisible by I, it means it is not prime. Otherwise, if after checking all the numbers, it was not able to divide any, it means that it's prime. Very simple. It's a very simple concept. Run a for loop and check it. That's it. Let me give another example. Okay, let's take another example. Let's take an example of the number 36. Okay, so 36, I know. Let's say if I write all the numbers that are dividing 36. Okay, I know 36 is not a prime number. Obviously, it's divisible by 2, and it might be divisible by some other numbers as well. Let's write it down. Another example. So if I'm saying 36 is divisible by which number? 1, first of all. So 1 into 36 gives me 36. It is also divisible by 2. 2 into 18 gives me 36. It's divisible by 3 also. 3 into 12 gives me 36. Why am I writing 36, 36 again and again? You get the idea. So 3 into 12. Then we have 4 into 9 gives me 36. Yeah, that's correct. 5, no. 6, yes. 6 into 6 gives me 36. That is correct. Right? 7, no. 8, no. 9, yeah. 9 into 4 gives me 36. Okay. 10, no. 11, no. 12, yes. 12 into 3 gives me 36. What all numbers divide 36? 13, no. 14, 15, 16, 16, no. 17, no. 18, yes. 18 into 2 gives me 36. 19, no. 20, no. And then I think only one remaining now is 36. 36 into 1 gives me 36. Okay. So what we are trying to see is, can you see that this and this is getting repeated? Can you see that? Can you see that this and this is getting repeated? The red that I have highlighted. If you are checking that 3 into 12 gives me 36 or whatever, do you need to check whether 12 into 3 also gives me 36? That's the question. If you're saying that 3 into 12 gives me 36, do you need to check whether 12 into 3 gives 36 or not? No. If you're checking 1 plus 2 is equal to 3, do you need to check what is 2 plus 1? No. This is just rearrangement. These are all rearrangements, the red ones of this. So this is repeated. Hence ignore. So instead of checking all the n minus 2 numbers, all the n minus 2 numbers, now you can only check these numbers, these ones. Hence, only make checks for numbers less than, less than square root of the number itself. Doesn't that make sense? Okay, so all numbers are less than equal to the square root of the number. We are only going to check for that. We are also able to ignore all of these because same thing. Isn't it cool? Right? Very cool stuff. This has reduced the complexity to what now? We are only checking the square root of n, that's it. Instead of n, our complexity is root n. How simple was this? I hope you are able to understand this thing. Let's try to code this. Or this entire array. If I XOR this entire array, I know that all. So I'm going to create another class over here. I'm going to say prime number or not. Okay. I'm going to say public static void main, and I'm going to create, let's say, another function. So it's going to be like static boolean. It's going to return whether it's prime or not, and it's going to be, let's say, is prime. It's going to take a number n. Okay. So I can say if the number n is less than equal to 1, obviously it's, 1 is neither prime nor composite. So I can just say return false. Make sense? After that, I can say I can start by dividing by 2. We are starting from dividing by 2. So I can say start from dividing by 2. So this I'm going to go till the square root only, right? So I'm going to say while c star c is less than equal to n. Okay, c star c is less than equal to means what? While c is less than equal to root n, I just squared both the sides. Basic mathematics, just to keep things simple. Okay, so here I'm saying if this number is dividing n, if n is divisible by c, just return false. That okay? This is dividing, hence it's not prime. Cool. Otherwise, what are we going to do? Otherwise, just increment the value of c. Okay, check for 2, check for 3, or whatever till square root of n. You can also write c less than equal to square root of n, but I just square rooted both the sides so that it becomes a much more clean code. Okay, it's very basic mathematics. If you want, I can explain it. No problem. Okay, so here these numbers, the ones that have 1, 2, 3, 4, 5, 6, all need to be less than equal to square root of n. So a number for which you are checking should be less than equal to, let's say, square root of n. Okay, if I just square both the sides, it means this. That's basically what I'm doing. Okay, and after running the entire loop, if it says that okay, no numbers divide, then you can say yeah, it's prime. Return true. You can try this. I can say int n is equal. Never mind. I can just say for int I is equal to. I can start with, let's say, 1. I can say I is less than equal to n and I plus plus. I can get int n over here something, let's say, equal to 20. Then I can say print. I can say I plus a space is prime or not. the duplicates will lead to 0. 2 XOR 2 will give me 0. Why? Because A XOR A gives 0. This will give me 0. This will give me 0. This will give me 0. And this will give me 0. Only thing remaining in the end will be what? 0 XOR 4. That will give me what? 4. That's your answer. XOR the entire array. That's your answer. In the end, you will be only be remaining with the element that is unique, because all the duplicate elements will be XORed by themselves. Order does not matter. Okay. In the end, if you have duplicate elements, they will get XORed and they will be equal to, I can say, is prime I. Let's see. So it's saying one is not prime, that's correct. 2 is prime, 3 is prime, 4 is not prime, 5 is prime, 6 is not prime, 7 is prime, 8 not prime, not prime, not prime, prime, not prime, prime, not prime, not prime, not prime, prime, not prime, prime, not prime. Yeah, it's works well. Alrighty, well, yeah, that was pretty cool. Square root of n, you were able to solve it. Okay, now let's look into a question. So the question states that, let's say you have something like, let's say you have something like, you're given a number n. So let's say n is equal to 40. Okay, you're given n is equal to 40. you have to find out all the numbers less than 40, less than equal to 40, that are prime numbers. What are all the numbers less than equal to 40 that are prime numbers? So the answer is we have 2, 3, 5, 7, 11, 13, 17, 19, 23, what else? 29, what else? 31, and 37. These are all the numbers less than 40 that are prime. That is the question. A number n is given to you. You have to find all the numbers less than n or less than equal to n that are prime numbers. How can we do this? Always when you're given an interview question, first come up to the brute force solution as soon as possible. Brute force means not very optimized, simple solution. One simple solution for this can be the same program we just wrote for prime numbers. We can check for that program for every number less than n. So first we can check for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 till 40. Is 2 prime? The program function will be like, yeah, it is. Is 3 prime? Yes, it is. Is 4 prime? No, it's not. So whenever we are getting over here, we can just say that, hey, just run up, just this is actually the one that we have solved just now. Find all the prime numbers less than equal to n. Oh, this is exactly what we have done so far. We can just start it from 2 instead of 1. So I can say if this is prime, then only display. But what is the complexity of this program? We know this particular function takes square root of n time. We are running this function n times. N into square root of n is the answer over here. N into square root of n. Can we do it in a much more optimized way? Can we do it in a much more optimized way? This thing that I just taught you, can we apply this approach of things getting repeated in this problem as well? For example, when you know, let's say you start from 2, when you know that 2 is prime, does it not mean that all the multiples of 2 will not be prime? So if you know that 2 is prime, do you need to check whether 2 2s are 4, 2 3s are 6, 2 4s are 8, this 4, 6, 8, 12, 24. Do you need to check whether these are prime or not? No, because these are multiple of 2. 2 is already dividing these numbers. then why are you making a check of these numbers in this for loop? Can there be a way to eliminate this check? Similarly, when you check for 3, 3 is a prime number, then do you need to check whether 9 is a prime number or not? Whether 12 is a prime number or not? Whether 18 is a prime number or not? Whether 21 is a prime number or not? Can you see that? One more thing you can note over here.